Okay, let's just jump right in. Close your eyes for a second, if you're not driving or something. Imagine the very fabric of reality. Everything,
Yeah.
every star, every galaxy. We're listening to this right now.
Yeah.
What if it wasn't born from some, I don't know, singular cosmic flash? That whole creation moment.
Mm-hmm. Where are you going with this?
What if our whole universe, this mind-bendingly huge thing, was actually forged in the violent collapse of some monster structure in another reality entirely?
Okay, wow. That's that's a hell of a thought experiment to kick things off. It really does twist your brain, doesn't it?
Right? That's the staggering, honestly kind of unsettling idea we're really going to wrestle with today.
And it flies right in the face of, well, decades of cosmology. Our standard picture, the Lambda CDM model, it's been our cosmic map, our guide.
Totally. And it's been incredibly successful.
Oh, unbelievably successful. It charts how the universe evolved with just breathtaking precision. It's a monumental achievement, truly.
There's always a but.
There's always a but. And it's a big one. This champion model, it stands on some really shaky, enigmatic foundations. We're talking dark matter, dark energy.
Stuff that makes up, 95% of everything, and we have no clue what it is.
Exactly. And then there's the big one, that completely baffling, physically impossible Big Bang singularity. These aren't just footnotes. They're huge, gaping holes in the theory.
And that's the tension, isn't it? So today we're diving headfirst into something really radical, maybe even audacious. Black hole cosmology.
Right. And this isn't just, physicists chatting after hours. This is a serious class of theories.
Theories proposing that our universe didn't just poof into existence from nothingness.
Correct, but that it actually emerged from inside a black hole that formed in a universe that existed before ours, a parent universe.
So the Big Bang wasn't Genesis, it was a big bounce.
That's the core idea, a transition, not a creation ex nihilo.
Okay, so our mission today in this deep dive is to really dissect this captivating, maybe disturbing idea. We'll dig into the theory behind it, the bold claims it makes about solving cosmology's biggest puzzles.
Like the singularity, dark matter.
Exactly. We'll look at the evidence, which, spoiler alert, is pretty thin and tricky to find.
And the criticisms, which are fierce.
Yeah.
Brutal, even.
So yeah, prepare to have your cosmic foundations maybe shaken up a bit.
It's definitely a trip into the speculative, but it's motivated by real problems in physics.
Yeah.
We need to scrutinize it properly.
Let's start with the king, Lambda CDM. You can't talk about alternatives without acknowledging the reigning champ.
Absolutely. You have to give it credit. It's mathematically precise, and it fits an astonishing range of observations. Like, incredibly well.
We're talking the CMB, right? The cosmic microwave background, that baby picture of the universe.
The CMB, precisely. Its structure is predicted beautifully. Then there's the way galaxies are spread out across the cosmos, this huge cosmic web.
Lambda CDM nails that too.
It nails that. And the amounts of light elements, hydrogen, helium created in the early universe, bang on.
And even the fact that the universe's expansion is speeding up now.
Yes, the accelerated expansion, driven by dark energy, or lambda. It's a massive achievement, no doubt about it, a testament to decades of work.
But, back to the but.
Back to the but. Despite these incredible triumphs, Lambda CDM is haunted by these profound unknowns.
Dark matter, dark energy. The big elephants in the cosmic room.
They make up almost all the universe's energy budget, yet we fundamentally don't know what they are. They're like cosmic placeholders. We see their effects, their gravity.
But the actual substance.
Blank.
An infuriating blank. They're the unseen puppeteers pulling the strings, but we can't see them. It's a massive gap in our understanding.
And then there's the origin point, the singularity. This is where it gets really weird, right? And maybe a bit unphysical.
That's the term physicists use, yeah. An unphysical premise.
Yeah.
The standard model starts with this gravitational singularity at time zero. Just picture it, a point, infinite density, infinite temperature, all the laws of physics we know, gone. Even Einstein's general relativity just breaks.
It completely shits the bed. It's like a cosmic divide by zero error at the very start. It's not just a puzzle. It's a fundamental breakdown.
A screaming sign that the theory is incomplete.
Absolutely. It tells us GR can't be the whole story, especially not at the very beginning. It's a wound in modern physics.
A wound we've been staring at for a long time.
Decades. And it's in response to these huge problems, the dark stuff, the singularity that black hole cosmology comes onto the scene.
Offering this, well, almost deceptively simple idea.
Right. What if our universe didn't just appear from nothing? What if it emerged from inside a black hole formed in an older, pre-existing parent universe?
Oh, unpack that. The Big Bang becomes a bounce.
Exactly.
Mhm.
It reframes it completely. Not a sudden creation, but a transition. A violent, sure, but maybe controlled rebound from an unimaginable state of collapse inside that parent black hole.
Exploding outwards into the expansion we see.
That's the picture. So for you listening, what does this mean? It means our cosmic beginning might just be a continuation, an echo of something older.
It gets rid of that need for a magical creation moment,
It replaces it with potentially an ongoing process, maybe even a cycle.
which is a profound shift. But, okay, let's be super clear here. We're not saying BHC is right or wrong.
Absolutely not. That would be jumping the gun massively for a theory on the absolute edge of physics.
What we're doing is a scientific audit. We're dissecting its logic, seeing if it could explain the mysteries, weighing the flimsy evidence.
In facing the tough criticisms head on, it's about giving you a balanced, deep look at an idea that's as fascinating as it is way out there.
All right, let's get into the guts of the theory. How do you even start building a universe from inside a black hole? It sounds like science fiction.
Well, the seeds were planted a long time ago, even before Einstein, actually. There was this 18th century English clergyman, John Michell.
A parson doing cosmology.
Yeah, a real thinker. Back in 1783, he figured if a star was massive and dense enough, its escape velocity would be faster than light, so it would be invisible. A dark star.
Wow. That's pretty close to the black hole idea, just using Newton's gravity.
Exactly. A prescient idea, though it kind of got lost for over a century. The modern black hole? That's pure Einstein. General relativity.
Published 1915, and almost immediately.
Within months, Carl Schwarzschild, working on the Russian front in World War I, unbelievably, finds the first exact solution to Einstein's equations.
The Schwarzschild solution.
Right. Describes the space around a static spherical mass, and it predicted this critical boundary, the Schwarzschild radius, the event horizon, point of no return.
We all know the event horizon, don't cross it. But the solution inside the horizon, that's where it gets really strange, right?
That's where things get properly bizarre. Mathematically, inside the horizon, the rolls of time and the radial coordinate distance from the center, they swap.
Swap, what does that even mean?
It's not just math games. It has a profound physical meaning. Outside, you're always moving forward in time. Inside, you are inexorably pulled towards the center, r as zero. That singularity isn't a place anymore. It's a moment in your future.
Like falling down a river towards a waterfall you absolutely cannot avoid.
Precisely. No matter which way you swim spatially, your future is the singularity. It's a chilling concept. You're literally crushed out of existence in finite time.
And for ages, this interior solution was just a mathematical quirk.
Pretty much, until 1972. A physicist named Raj Pathria noticed something. He saw a striking mathematical similarity between that interior Schwarzschild solution and the standard model for our expanding universe, the FLRW metric.
Wait, the inside of a black hole mathematically resembles our entire universe?
In a specific way, yes. Pathria showed that if you equated our universe's Schwarzschild radiuses, calculated from its total estimated mass energy with its actual observable size, its properties looked mathematically like it could be the interior of a black hole.
That's a hell of a leap. From a weird bit of math inside a star to the whole damn cosmos.
It ignited the whole idea of Schwarzschild cosmology. It was the spark.
So singularities are key here. Let's nail this down. What is a singularity in physics? It's not a thing, right?
No, not a physical object. It's a point where your theory goes haywire, where the mathematics predicts infinity's infinite density, infinite space-time curvature. It's the theory screaming, I can't handle this, my equations break down here.
It's a failure point in the model.
Exactly. It signals we need a deeper theory, usually involving quantum gravity, which we don't have yet.
And general relativity, our best theory of gravity, predicts these infinities in two places.
Two very crucial places, yes. At the heart of black holes, where matter gets crushed infinitely, and at the very beginning of the universe in the Big Bang model.
The same mathematical breakdown at the cosmic start and the stellar end, that seems significant.
Many physicists think it's hugely significant. Not a coincidence, but a deep clue. A sign that these two endpoints might be related, or that GR is failing in the same way in both extreme regimes.
And this is where BHC makes its move. It says, what if these aren't two separate problems?
Precisely. What if the Big Bang singularity is a black hole singularity? Or rather, what if what we think is a singularity in both cases is actually something else about?
Killing two birds with one stone.
That's the elegant proposal. It reframes cosmic history. It connects the beginning and the end. The motivation isn't just random speculation. It's trying to fix a known fundamental problem in physics. A damn clever attempt, really.
But to make this work, you need to avoid the infinite crush. You need a mechanism for the bounce. How do you do that? Classical GR says collapse is inevitable.
You need new physics. You need something to step in and halt the collapse. Several ideas have been proposed, some leaning on established physics, others more out there.
Give us the front runner.
Okay, the most developed model probably comes from Nikodem Popyevsky. His work uses something called Einstein-Cartan-Siama-Kibble theory, or ECSK gravity.
Kitschy name.
Yeah.
How's it different from regular Einstein gravity?
Standard GR assumes space-time curvature is symmetric. ECSK allows for asymmetry, introducing something called space-time torsion. Think of it like adding a twist to the fabric of space-time, not just a curve.
A twist. Sourced by what?
By the intrinsic spin of fundamental particles, electrons, quarks. Popyevsky's big idea is this. Normally, this torsion effect is minuscule, totally negligible.
But inside a collapsing star.
At the absolutely insane densities involved way beyond nuclear density, this spin-torsion interaction becomes incredibly powerful. And crucially, it acts as a repulsive force.
Repulsive, pushing outwards against gravity.
Exactly. Like a giant cosmic spring, it violently opposes gravity's crush, halting the collapse at a finite, though still immense density. Maybe an element in 96 kilometer. This is a stupidly large number.
Okay, so collapse stops. Then what?
Then it rebounds. Explosively. That's Popyevsky's big bounce. The black hole doesn't lead to a singularity, it transforms into a bridge.
A wormhole. An Einstein-Rosen bridge.
That's the idea. A non-singular gateway connecting the parent universe to a brand new, rapidly expanding baby universe forged in that bounce. It's mind-bending stuff.
Seriously. Are there other ways to get a bounce?
Yeah, Popyevsky's isn't the only game in town. Others have looked at quantum mechanics. Enrique Gastineaga suggested the Pauli exclusion principle.
The thing that stops electrons stacking up in atoms.
That's the one. No two identical fermions in the same state. At extreme densities, maybe this creates a huge outward degeneracy pressure, stopping the collapse. The appeal is it uses known physics, but applying it here is purely theoretical.
Any other ideas? Maybe weirder ones?
Oh, yeah. Some propose interactions between gravity and other fields, like the Higgs field, might become repulsive at ultra-high energies near a would-be singularity. Lots of theoretical exploration.
So the main point is the bounce itself, not necessarily how it bounces.
That's the core concept. The specific physics is still up for grabs, which, shows flexibility but also highlights the speculation involved. Popyevsky needs ECSK to be right, not just a mathematical toy. That's a big if.
And then someone took this universe birthing idea and ran even further with it. Darwin in the Cosmos.
Lee Smolin. Cosmological Natural Selection, or CNS, sometimes called fecund universes. It's Darwinian evolution applied to the multiverse. Utterly audacious.
Trying to explain fine-tuning why the universe's constants seem perfect for life.
Exactly. That's one of the biggest mysteries. Why are things like the electron's charge or gravity's strength just right for stars, galaxies, and us to exist? Smolin's CNS tries to answer that.
Now, what are the rules of this cosmic evolution?
3 core ideas, all pretty unsettling. 1, reproduction. Every black hole makes a new baby universe inside it.
Okay, that's the DHC mechanism we just discussed.
2, mutation. When a new universe is born, its fundamental constants, speed of light, Planck's constant, etc., vary slightly, randomly, from the parent's values.
Like genetic mutation, but for physics laws?
Kind of.
Yeah.
And 3, selection. Universes whose physical constants make them better at producing black holes will have more offspring universes.
So universes that are good at making black holes reproduce more.
Over countless generations, Smolin argues, natural selection favors universes optimized for black hole production.
And his controversial conclusion.
Our universe's constants should be optimized for making black holes. And here's the really wild part. He argues the conditions needed for making lots of black holes, like long-lived stars making heavy elements, lots of carbon, happen to be the same conditions needed for life.
Whoa! So life isn't the point, it's just a side effect of optimizing for black holes.
That's the provocative claim. It tries to explain our life-friendly universe not as a fluke or design, but as an evolutionary outcome. This is the absolute outer edge of speculation, though. It needs the bounce mechanism plus this unproven meta law about mutating constants. It's a breathtaking idea.
Okay, let's shift gears. We've built the theoretical structure. What's the appeal? Why is this idea so seductive? Beyond just being weird and cool, what problems does it claim to solve?
Well, the biggest one is that absolute beginning problem. The standard Big Bang starts at time 0 with a singularity. It gives absolutely no account of what came before or why it even happened. Physics just stops.
It's a brick wall.
A total brick wall. BHC steers that down and says, there was no absolute beginning. Our origin isn't creation from nothing. It's a transition within an eternal process.
Our Big Bang is just the result of a black hole collapsing in a previous universe.
Yeah, exactly. It immediately reframes our entire cosmos as just one link in a potentially infinite chain of cosmic generations. It removes that awkward first moment.
And this leads naturally to a multiverse, right? But a specific kind.
Yes, a genealogical multiverse. Not like string theory's maybe disconnected bubbles. This is a cosmic family tree. Every black hole in our universe could be seeding a new one. We were a child of a parent universe's black hole.
Could these universes interact?
Potentially. Smolin and others have speculated. If two black holes merged in the parent universe, maybe their child universes show effects. Maybe large-scale patterns in our CMB could be scars from interactions with sibling universes. It paints a picture of a dynamic, interconnected cosmic ecosystem, much more interesting than just popping out of nowhere.
Okay, origins aside, what about other deep puzzles? Like time's arrow. Why does time only flow one way?
BHC offers some interesting perspectives there, too. Popowski's model, for example, links it to the black hole's event horizon. That horizon is a one-way street, right? Matter falls in, never comes out.
A cosmic bouncer, yeah.
He proposes that this inherent directionality, this one-way causal structure of the parent black hole, gets imprinted on the baby universe born inside. So the arrow of time in our universe could be a direct inheritance from the irreversible collapse in the parent universe.
Giving time's flow a physical anchor? That's neat. What about the information paradox, Hawking's big problem?
The black hole information paradox.
Yeah.
A massive headache for physicists. It comes from combining general relativity and quantum mechanics. Hawking calculated that black holes evaporate over time, emitting radiation.
Hawking radiation.
Right. But this radiation seems random, thermal. It doesn't seem to contain the information about what fell into the black hole. So when the black hole evaporates completely, is that information just gone, destroyed?
Which violates a fundamental rule of quantum mechanics. Information is never truly lost. Unitarity.
Exactly. It's a brutal contradiction between our two best theories. A real thorn in the side for decades.
And BHC has a solution.
A radically simple one. It says the information isn't destroyed or encoded in the Hawking radiation. It just passes straight through the bounce into the new baby universe.
Whoa. So everything that fell into the parent black hole helps shape the new universe.
That's the proposal. Solves the paradox neatly. But it's fiercely debated.
Why?
Because many other leading physicists, like Leonard Susskind, argue strongly that the information must escape with the Hawking radiation back into the parent universe. They have sophisticated arguments based on things like holography.
And it can't do both?
Nope. Information can't be in two places at once. It either escapes back to the parent or passes through to the child. These solutions are mutually exclusive.
So BHC's answer to the information paradox stands or falls with the ultimate resolution of this incredibly deep debate in quantum gravity. We just don't know who's right yet. Okay, this is getting ambitious. Solving origins, time's arrow, information loss. What about the really big observational mysteries? Dark matter and dark energy. Does BHC have anything to say about them?
This is where it gets really ambitious. Some proponents claim it could potentially explain both. Let's start with dark matter.
The invisible stuff holding galaxies together, 85% of all matter.
Exactly. The idea is that the incredibly violent particle production during the Big Bounce could naturally create a huge number of primordial black holes, or PVHs.
Black holes formed right at the beginning, not from stars.
Yes, formed from density fluctuations in the ultra-early universe. PVHs have been a candidate for dark matter for a long time. BHC provides a potential natural mechanism for making them right at the universe's birth, tying the solution to the singularity problem directly to the dark matter problem.
Okay, that's elegant. One process, two solutions. What about dark energy, the accelerating expansion?
Even more speculative, but some models go there. In Popowski's torsion model, remember, the parent black hole could be rotating. Most big things in space do rotate.
Stars, galaxies, they spin, so the black hole they form would spin too.
Right. If our universe was born inside a rotating black hole, it would inherit that rotation, setting up a preferred axis in the cosmos.
Yeah.
Popowski theorizes that on the very largest scales, the centrifugal force from this cosmic rotation would act like a uniform repulsive pressure.
A repulsive pressure pushing everything apart, like dark energy.
Exactly like dark energy. It could potentially explain the accelerated expansion without needing to invoke this mysterious cosmological constant, lambda, with its bizarrely fine-tuned tiny value.
Okay, hold on. This theory potentially solves the singularity, anchors time's arrow, resolves the information paradox, and explains both dark matter and dark energy. That sounds
Okay,
almost too good to be true.
that's the skeptical reaction, and it's a healthy one. The sheer explanatory power is dizzying, incredibly alluring. It promises this beautifully unified cosmology. But a theory that explains everything risks explaining nothing. It can become too flexible, too hard to falsify. Take the dark energy explanation. It relies on our universe inheriting spin. The main evidence cited for that is an observed asymmetry in galaxy spins.
Uh-oh. Circular reasoning alert?
Potentially, yes.
Yeah.
Spin asymmetry proves cosmic rotation, which proves the BHC model that predicted it based on inherited spin. You need independent verification for each step in that chain. Otherwise, the impressive scope could just be a sign of how speculative it is, not how right it is. It's a huge red flag.
Right. Theory is one thing, but science lives and dies by observation. Let's get into the harsh light of evidence. What faint fingerprints might BHC leave on the cosmos?
This is where it gets really tough for BHC. The evidence is, well, let's say suggestive at best, and highly contested.
Start with the big one. The cosmic microwave background, the universe's baby picture.
The CMB, our most precise cosmological probe. It's the faint afterglow of the Big Bang, around 380,000 years after the start. Almost perfectly uniform heat, but with tiny temperature fluctuations.
And standard cosmology plus inflation nails the pattern of those fluctuations spectacularly well.
Phenomenally well. So rule number one for any alternative like BHC, you have to reproduce that success. You have to be consistent with the CMB data. Proponents like Popowski argue their bounce models can generate an inflationary period consistent with the Planck satellite data.
Okay, so consistency is possible, but does BHC predict anything unique in the CMB? Any smoke and guns?
In principle, yes. If our universe inherited rotation, maybe that leaves a large-scale pattern of preferred axis imprinted on the CMB. If we interacted with a sibling universe early on, maybe that leaves a weird cold spot or some other anomaly.
And have we seen any anomalies like that?
Well, tantalizingly, yes. Cosmologists have found some weird large-scale features in the CMB data that don't perfectly fit the standard model's predictions. There's a hemispheric bias. One half of the sky looks statistically slightly different from the other, and the largest patterns, the lowest multipoles, seem weirdly aligned with each other and with our solar system's plane, the infamous axis of evil.
Axis of evil. Sounds dramatic. Is this the proof BHC needs?
Not so fast. Here's the massive caveat. The statistical significance of these anomalies is hugely debated. Are they real signals of new physics? Or just statistical flukes you'd expect to find eventually in a massive data set? Or could they be subtle contamination from dust in our own Milky Way that we haven't perfectly subtracted?
So nobody agrees if they're real.
Basically, no. There's no consensus at all. Not a single CMB anomaly is widely accepted as definitive proof of any new physics, let alone BHC specifically. So this whole line of evidence remains frustratingly inconclusive. A hint, a maybe, but nothing solid.
Okay, what about that cosmic rotation idea? Is our universe actually spinning? That seems like a more direct test.
This is probably the most provocative, potentially explosive claim relevant to some BHC models. Standard cosmology, based on the cosmological principle, says the universe should be isotropic the same in all directions.
Meaning galaxy spin should be totally random, 50-50 clockwise versus counterclockwise.
Exactly. But several large studies looking at galaxy surveys have thrown a spanner in the works. Data from Sloan, and more recently from the James Webb Space Telescope, have reported a statistically significant asymmetry.
Not 50-50.
One JWST study of very early galaxies reported something like a 60-40 split favoring one direction. That's hard to explain away purely by chance if the measurement is robust.
And BHC proponents would say.
Smoking gun. If our universe was born inside a rotating black hole, it inherits that spin. That preferred cosmic axis influences how gas clouds collapse to form galaxies, leading to exactly this kind of spin alignment. It fits their narrative beautifully.
Sounds compelling. What's the catch this time?
The catch is, again, systematic errors, observational bias. Could the asymmetry be an illusion caused by how we observe these galaxies from our own rotating galaxy? Maybe the Doppler effect makes galaxy spinning one way look slightly brighter, so we detect more of them in deep surveys.
A local measurement artifact, not a global cosmic property.
That's the big counterargument. We need to be absolutely sure we've accounted for all possible observational biases before claiming the universe itself is spinning.
And even if it is spinning, does that automatically prove BHC?
No, not necessarily. It might just mean the cosmological principle is an approximation, not absolute truth. Maybe the universe does have a slight rotation for other reasons. Kurt Gödel even found solutions to Einstein's equations describing rotating universes way back in 1949.
And you mentioned this could connect to the Hubble tension.
Right, some researchers are exploring if a slowly rotating universe could help resolve that discrepancy in the expansion rate measurements. So there are independent reasons to investigate cosmic rotation. It's not uniquely tied to BHC, which weakens it as definitive proof for BHC. It's suggestive but not conclusive.
Okay, let's talk about that numerical coincidence. The Schwarzschild radius of the universe matching its observable radius. That sounds pretty striking.
It does on the surface. You take the estimated mass energy of everything in the observable universe, plug it into the formula for a black hole's event horizon radius.
And you get a number remarkably close to the actual size of the observable universe, about 46 billion light years.
Yep. It's an old argument, often brought up. To BHC proponents, it's a huge clue. See?
Oh.
The universe fits the description.
But the mainstream view is?
The mainstream view is, this is numerology, a misleading coincidence, a red herring.
Why?
Because the Schwarzschild solution describes a very specific physical situation. A mass concentrated at the center, creating a strong local gravitational field in an otherwise flat background. Our universe isn't like that at all.
It's homogeneous on large scales.
Yeah.
Matter everywhere. No central point.
Exactly. The gravitational pull is roughly equal in all directions. The physical conditions needed to actually form a black hole event horizon just aren't met by the universe as a whole.
So why the numerical match?
Critics argue it's simply because both calculations, the Schwarzschild radius and the Hubble radius, related to the observable universe's size, depend on the universe's mass and fundamental constants in similar ways. So getting similar numbers isn't profound. It's almost mathematically inevitable given the inputs. It's a trick of the formulas, not deep physics.
Okay, so CMB anomalies are debated, rotation is debated, the radius coincidence is likely just math. What about finding actual relics left over from the Big Bounce?
That's another avenue. If the bounce was a real violent event, it should have left stuff behind. The main candidates are primordial black holes, PBHs.
The dark matter candidates we mentioned.
Right. The extreme conditions of the bounce could have squashed dense regions into black holes before stars even existed. Searching for these PBHs is an indirect way to test bounce scenarios.
How do we look for them?
Looking for gravitational lensing tiny distortions of starlight as a PBH passes in front, or listening for gravitational waves from merging PBHs with detectors like LIGO and Virgo.
And have we found them? Is dark matter solved?
We found merging black holes, yes. Some around 30 solar masses, which is interesting because that mass range is a bit tricky to explain with normal stellar evolution, potentially hinting at a primordial origin. But all the searches so far have put really tight limits on how many PBHs can be out there across most possible masses. Current data suggests they could only make up a small fraction of dark matter, maybe a few percent at most. Definitely not all of it.
So that creates tension for BHC models that wanted PBHs to be the dark matter.
Significant tension, yes. It doesn't rule out the bounce, but it makes it harder for BHC to claim it solves the dark matter problem cleanly.
Is there any other predicted relic? Something unique to BHC?
There is one. A single primordial white hole.
The opposite of a black hole. Stuff only comes out, can't go in.
Exactly. The time reverse solution. In the BHC picture, this white hole would be the other end of the wormhole connecting us to the parent universe, the exit point.
Finding that would be game over. Proof positive.
It would be incontrovertible proof.
What do you?
Here's the soul-crushing catch.
Oh, no.
By its very nature, a white hole is likely unobservable and untestable. How would you trace a signal back to something nothing can enter? Its properties are purely theoretical constructs.
So the most testable prediction, PBHs, is constrained, and the most unique prediction, the white hole, is untestable.
That pretty much sums up the observational frustration for BHC. It's a cruel cosmic joke, in a way.
All right, let's move to the direct criticisms. The arguments against BHC from the mainstream, what are the biggest hurdles?
The most straightforward, maybe most brutal argument, especially against simpler BHC ideas, is just looking at what we see. The universe we live in looks absolutely nothing like the inside of a classical black hole described by general relativity.
How so?
Standard cosmology, lambda CDM, rests on the cosmological principle. The universe is homogeneous and isotropic on large scales. Same everywhere, looks the same in all directions. Observations back this up incredibly well.
And a black hole interior.
It's the exact opposite. It's fundamentally anisotropic. It has a special point, the singularity that everything must fall towards. There's a definite direction, a center. Our universe doesn't seem to have that.
And geometry, we measure the universe to be flat.
Extremely close to flat, yeah.
Yeah.
Decades of CMB data confirm this. Flat, like a sheet of paper on cosmic scales. The Schwarzschild solution, meanwhile, describes intensely curved space-time, like a deep funnel.
So they just don't match up.
On the surface, not at all. Now, BHC proponents, especially the more sophisticated ones like Popwiowski, have a response here.
Which is?
They aren't saying we live inside a classical GR black hole. Their whole point is that new physics inside the black hole, torsion, quantum effects, whatever, prevents the singularity and triggers a bounce into a new universe that is homogeneous, isotropic, and nearly flat.
Ah, so the argument isn't, does our universe look like a known black hole interior?
No. The argument shifts to, are black holes actually portals, where new physics creates universes that look like ours? It pushes the whole debate into the realm of quantum gravity physics we don't have experimental access to. So the accuracy of BHC depends entirely on this radical, unproven reimagining of black hole interiors.
Okay, another criticism I've heard involves confusing different kinds of horizons. How does that work?
Yeah, this is a subtle but important point, especially in how BHC gets portrayed in popular science. Critics argue it gains a lot of its intuitive appeal by muddying the waters between two very different concepts.
The black hole event horizon?
And the cosmological horizon. They sound similar, but they're fundamentally different beasts.
Remind us, black hole event horizon.
That's a causal boundary.
Yeah.
A real physical point of no return created by intense local gravity. Cross it, and you can't escape back out. Your future is inside.
And the cosmological horizon.
That's an observational limit. It exists purely because the universe has a finite age, 15.8 billion years, and light travels at a finite speed. We can only see things whose light has had time to reach us since the Big Bang. It's a limit on our knowledge, not a physical barrier trapping us. Someone in a distant galaxy has their own different cosmological horizon.
So, equating the two
Is a category error, critics say. The argument that the Schwarzschild radius coincidence is meaningful relies on treating these two different horizons as somehow equivalent. The physics is totally different, local gravity versus global expansion and light speed. So that numerical similarity, dismissed as meaningless coincidence, a clever trick, not physics.
What about things we should see if we were inside a classical black hole but don't?
Right. If you ignore the new physics argument for a moment and just take the classical interior, well, things look bad. First, spaghettification.
Getting stretched and squeezed by tidal forces.
Exactly. Objects falling into a black hole experience extreme tidal forces near the singularity. An observer inside should feel these immense gravitational gradients. Our universe, on large scales, is incredibly smooth and gentle. No universal cosmic stretching.
And the direction of travel.
This is maybe even more damning for the simple picture. Inside an event horizon, everything must move towards the central singularity. All paths converge. Yet we see the exact opposite.
Hubble's law. Distant galaxies are all moving away from us. Expansion.
Exactly. We can send probes like Voyager out in opposite directions, and they both just keep going away. That seems utterly incompatible with being trapped inside a gravitational well, pulled towards one point. Now again, the bounce proponents say the bounce creates an expanding space.
But that just reinforces the point that they're not talking about a standard black hole interior anymore. They need new physics to make it work.
Precisely. They are describing something else entirely.
Beyond observations, are there purely theoretical or philosophical problems?
Oh yes, big ones. Causality is a major headache. In GR, the singularity inside a black hole is in the future of anything that falls in.
Cause has to precede effect.
Right, so the collapse of the star in the parent universe causes the bounce and the formation of the baby universe. The baby universe cannot cause the black hole to form in the parent because that would require information going back in time.
So you get this weird loop.
Where each universe is caused by its parent, but is the cause of its children. It's this seemingly illogical causal structure that some physicists find deeply problematic, maybe even paradoxical. A cosmic snake eating its own tail.
What about falsifiability? Can these theories make predictions we can actually test and potentially prove wrong?
That's crucial for any scientific theory. And here, Lee Smolin's cosmological natural selection model took a major hit.
How so?
Back in 1992, Smolin made a concrete, testable prediction based on his model optimizing for black hole production via neutron stars. He predicted the maximum mass of a neutron star couldn't be more than about 1.6 times the mass of the sun.
And what have we found since?
We've confidently observed neutron stars with masses of 2 solar masses, even slightly higher, directly contradicting his prediction.
Ouch. That's pretty bad for the theory.
It's a significant blow. You can always try to modify a theory, but when a core specific prediction fails, it severely damages its credibility. It undermines the whole premise.
And that CNS model also had that meta-law problem.
Yes, the meta-law dilemma. The theory needs this overarching rulebook dictating how physical constants mutate between universes. But for the whole evolutionary process to work and select for anything useful, that meta-law itself has to be just right. It needs to produce small, stable variations.
So it just pushes the fine-tuning problem up one level. What fine-tuned the meta-law?
Exactly. You potentially end up with an infinite regress of explanations, which is precisely what the theory was trying to avoid in the first place. It doesn't really solve the fundamental why question. These theoretical weaknesses are serious, suggesting that even if BHC overcame the observational hurdles, it might still be built on shaky logical foundations.
Okay, we've been through the theory, the potential solutions, the evidence, the criticisms. Let's try to pull it all together into a nuanced verdict. How does BHC stack up against the reigning champ, lambda CDM?
It's a study in contrasts, really. Lambda CDM is undeniably a phenomenological triumph. It fits the data incredibly well. It describes how the universe looks and behaves with stunning precision.
But it doesn't explain the why behind its key ingredients. Dark matter, dark energy. They're just put in by hand.
Exactly. Their fundamental nature is unknown. The descriptive blueprint, incredibly useful, but maybe not a deep explanation of origins.
Whereas BHC models try to be explanatory.
Fundamentally, yes. They aspire to give a deeper physical reason for why the universe is the way it is, deriving inflation, maybe dark matter, from the bounce dynamics, trying to explain the beginning.
But that explanatory ambition comes at a huge cost.
A massive cost. You have to introduce new, unproven physics torsion, specific bounce mechanisms. These models are way less developed, can't match lambda CDM's precision, and face their own serious theoretical problems we just discussed.
So it's a trade-off. Potential explanation versus current precision and observational grounding.
That's the state of play right now, yes.
So where does this leave BHC in the scientific landscape? Is it mainstream? Is it fringe? Is it pseudoscience?
Okay, let's be crystal clear. Black hole cosmology is not a mainstream theory. Not even close.
The vast majority of cosmologists work within lambda CDM.
Absolutely. It's the standard, most successful framework we have. If you look at official outreach from places like NASA, they'll explicitly say black holes aren't wormholes or portals, reflecting that institutional caution about this kind of speculation.
But that doesn't make it pseudoscience, right?
Not for a second. The leading proponents, Popbelski, Smoling, Gus, and Yaga, these are serious, respected physicists publishing in peer-reviewed journals. They're doing legitimate, though difficult, scientific work, proposing alternative ideas to tackle known problems in the standard model.
It's speculative, but theoretically motivated.
Deeply motivated by real physics problems like the singularity. The trouble often comes with the popular media representation. You see headlines screaming, "Scientists prove we live in a black hole," which is wildly misleading about the theory's actual standing.
So it's fringe, but legitimate scientific exploration.
That's the fair description. It's on the wild frontier of theoretical cosmology, not yet a paradigm competing on equal footing with lambda CDM.
And what's the future? How will we ever know if there's anything to this? Will it always just be speculation?
Ultimately, the future will be decided by data. Cold, hard, unforgiving data. Not just elegant math or philosophical arguments.
Where might that data come from?
Several places. Gravitational wave astronomy is huge. LIGO, Virgo, KHURI, listening to black hole mergers. Especially the ring-down phase, when a newly merged black hole settles.
Testing general relativity in extreme conditions.
With incredible precision. Any deviation, any tiny wobble from GR's predictions in that ring-down signal could crack open the door for alternative gravity theories like ECSK, which Popyowski uses. That would be massive.
What about actually seeing near black holes? The Event Horizon Telescope.
The EHT, yeah. They gave us those amazing first images. They want sharper pictures, even movies, of the region right outside the event horizon. Maybe subtle details in the shape of the black hole's shadow or the light swirling around it could distinguish a standard GR black hole from the non-singular objects some BHC models predict.
And just better cosmology in general.
Precision cosmology, exactly. Future telescopes like Euclid, Next-gen CMB surveys, they'll measure the universe's large-scale structure and geometry with even more mind-boggling accuracy. They could definitively nail down whether the universe have a tiny bit of curvature or if it's really rotating. Those would be decisive tests for specific BHC predictions. Data will be the judge.
Okay, so let's try to wrap this up. The headline idea: we live inside a black hole. Is it accurate?
Accurate in the sense of scientifically verified fact? Absolutely not. It remains a highly speculative, though theoretically fertile, hypothesis.
Is it theoretically coherent? Does it hang together logically?
It's a mixed bag. It offers this grand, elegant narrative connecting deep problems. But that elegance relies on introducing unproven physics like torsion or untestable ideas like the metal law for constants. So coherence is debatable,
It's explanatory power. That seems to be its big selling point.
without a doubt. That's the siren song. The potential to solve the singularity, drive inflation, explain dark matter and dark energy in one go. Intellectually, that's incredibly compelling. A potential theory of everything's self for cosmology.
But observational viability, the actual evidence?
Currently very low. Frustratingly low. The hints cited CMB anomalies, galaxy spins are ambiguous, indirect, heavily debated, and face strong counterarguments. It hasn't made a single unique, confirmed prediction. A smoking gun remains elusive.
And meanwhile, Lambda CDM, for all its flaws, just keeps racking up observational wins.
Precisely. The simpler model continues to fit the data remarkably well.
So what's the ultimate value of BHC then, if it's probably not right and the evidence isn't there?
Its value might not be in being correct. Its value lies in being a theoretical laboratory, a crucible. It forces physicists to seriously grapple with the consequences of quantum gravity, to question fundamental assumptions about time, about origins, about the uniqueness of our universe,
It pushes the boundaries of imagination.
and eventually, maybe, what can be tested. It's a testament to that relentless scientific drive to understand not just how the universe works, but why it's here at all, even if the answer turns out not to be inside a black hole.
We've just taken one hell of a deep, sometimes unsettling plunge into black hole cosmology, an idea that really messes with your standard picture of the Big Bang and our place in it all.
From black hole interiors birthing realities to universes evolving like life forms, it's been quite the ride.
We've seen its incredible ambition, its potential to explain so much, and we've seen its frustrating lack of hard proof.
The gap between theory and evidence is vast.
So, what does this mean for you, listening right now? It means the universe is likely far stranger, far more magnificent, and maybe far more interconnected than we usually allow ourselves to think.
Just consider it. What if our beginning wasn't the beginning? What if it was just an echo, a rebound from something incomprehensibly older, larger?
What if those terrifying black holes aren't cosmic dead ends, but cosmic wombs, continuously birthing new universes, with ours just being one branch on an infinite cosmic tree?
It's a thought that should make your brain ache, hopefully in a good way. A truly mind-expanding possibility.
The universe is definitely not done surprising us, not by a long shot. So keep asking the big damn questions. Keep pushing the edges of what seems possible.
Because as we've explored today, the truth might just be weirder, wilder, and more wonderful than any fiction we could invent. The biggest discoveries could still be lurking just over our current cosmic horizon.